So now we're going to be looking at specific gravity. Specific gravity is a measurement of density. So for example, 2 pounds of gold, if you were to throw it in some water, it would sink immediately because it's very dense. You would take 2 pounds of wood and you would throw it in some water and it would float, and that's because it's not very dense relative to the gold. Now, wood has different specific gravities. For example, Douglas fir larch, which is what practically every house is made out of from the mud sill up, is Douglas fir larch, and it has a specific gravity of 0.5. Now, the other thing wood we work with is old growth redwood, which is also called close grain redwood, which has a specific gravity of 0.44. And then we also have specific gravity of new growth redwood, which is called open grain, and that's 0.37. So we need to look at all those different types of wood and the specific gravity and see how it impacts the fasteners. And fastener, I mean a bolt, I need a lag screw, I need a nail, it's a staple, anything that connects two pieces of wood together. The first thing we need to be aware of is what the specific gravities are. So for Douglas fir, it's 0.50. And the reason Douglas fir is so important is that that is our baseline. Everything is based on that, in that all the tests that were done on hardware have always been on Douglas fir. And then if you change it to a different type of hardware, I mean a different piece of wood, if you go from Douglas fir to redwood, let's say, you have to use a multiplier so that you can do a conversion to see what the strength would be in redwood. We mostly use old growth redwood, which is called close grain redwood, or we use open grain redwood, which is your newer stuff, about 1945 on. You can tell because it's only 1.5 inches thick rather than the full 2-inch that you see in the old growth. The old growth close grain redwood is 0.44. The new growth redwood is at 0.37. And the way the multiplier is figured out is we take the old growth, which is the 0.44 that we have right here, we divide it by the specific gravity of the Douglas fir, and we get 0.88. Same thing for the new growth. We just take the new growth specific gravity of 0.37, divided by the old growth, by the redwood, the Douglas fir, and we get 0.74. So let's see how this works in practice. So we have a 10 penny nail, 1.5 inch penetration. We've got, in Douglas fir, it's 188 pounds of earthquake resistance it provides. And so what we do is we take that, we're going into redwood now, so we go with our redwood multiplier, which is right here. We go 0.88 into 188 pounds, we get 165 pounds. And so what that means is that nail can actually resist 165 pounds when it goes into old growth redwood. So all things being the same, just change one of the pieces of wood to old growth redwood, and then you have a new value. So the same thing if we have a toenail, and it's where it's rated 120. If we multiply it times 0.88, we end up with 106. So this actually has a pretty big impact on bolt capacities. So we're going to take a look at that right now. So here's a 1/2 inch bolt. Here's an 1.5 inch sill. That's what you would find in Douglas fir, this is to be your pressure treated wood. You don't see Douglas fir in sills until it's pressure treated, because when you touch wood to concrete, it's got to be treated to keep it from rotting, because redwood is naturally resistant to decay. So pretty much anything, if it's 1.5 inches, it'll be that's the only time we find Douglas fir is when it's pressure treated. Now in the 1.5 inch sills, we do see a lot of redwood houses built between 1945 and before pressure treated came in. I'm guessing that's about 1975 or so, I'm not really sure. But we'll also see redwood mud sills that are open grain. They're not old growth, they're open grain. The way you tell is if they're only 1.5 inches thick. So what we have here is we have a bolt in Douglas fir. It will resist 1,037 pounds, but when we go into the open grain redwood, it ends up being 912. So it's very similar. If we have a 1/2 inch bolt with an MSP, it's 1340. And the reason we can have that is because the original tests were done in Douglas fir, so that's exactly what we have, but we have to make a reduction. We multiply that times our 7.74 and we get this. And you can just go on down the line. Basically everything along here You multiply it times 0.74 because you're in open grain redwood, and you end up with these numbers right here. Now I wanted to show you this one right here because it shows the impact of the thickness of the wood that the bolt's in. So this is a 3x. Now a 3x naturally that's 2.5 inches rather than 1.5 inches as far as the sill goes. And because of that, there's more bolt that is actually touching the wood. So you have 2.5 inches of wood touching the bolt rather than just 1.5 inches. And that has a dramatic impact on the ability for a bolt, for the wood to resist an earthquake. So when the earthquake force is pushing on the bolt, there's 2.5 inches that are pushing on it rather than 1.5 inches. And what that ends up meaning is that the 3x material does not split until it gets to 1,890 pounds. And that's a lot. So in a situation like this, you could actually be building a shear wall. Let's say it's 10 feet long. It's designed to resist 5,500 pounds, and you could actually just put in 3 bolts rather than 5 or 6. Or sometimes contractors, engineers, they just throw things out. Go, just put in one every 2 feet or every 16 inches. They never actually do any engineering. So if you were to actually engineer something like that, you could just put in 3 bolts and you'd be done. You don't have to worry about anything else. So that's why these, knowing these multipliers, the thicknesses of wood, etc., is so important. So let's go ahead and look at bolts in 2-inch sills. So all the 2-inch sills are made out of redwood. We're not going to find a Douglas fir sill that's made out of. We're not going to find a Douglas fir sill made out of Douglas fir. So in those values, we have a 1/2 inch bolt. It can resist 1,109 pounds. And we just go on down the line. These are all the values that we took our load calculator and we figured out what those are. So we're going to go into some, these are plates, a URFP. It's a plate that we bolt to the side. It's a bolt substitute. And the exact same thing we have going on here. So it can resist 1,530 pounds. We go into old growth redwood. We multiply that times 0.88, and we end up with a value of 1,346. Now, if you look in the catalog, you're going to see this 1,530 value right here. And that's because all the tests were done in Douglas fir. You have to know to multiply it by these reductions, is what they're called, because of specific gravity. You just have to know how to do that. And if you don't know how to do that, you don't know what that you need to do that, you're going to end up with a retrofit that's not what it should be, because you're using the wrong values for your calculations. So same thing here. We have a URFP as we reach 1,530, but we're going into the new growth redwood, and we end up with 0.74. The bolt can only resist the URFP can resist 1132. And we go down here, we have the exact same thing. A UFP, which is the older style, is UFP 10 in the Douglas fir, resists at 1340. We multiply that times 0.88, 1179, and then we go on down here for new growth redwood, and we get 0.74. Now the reason I'm bringing up this part right here is, let's say you're doing a retrofit and you find that there's some UFP 10s in there, and you want to know, well, hey, how strong are the UFP 10s? I want to count those in my retrofit because you don't want to replace them or waste them. So you just want to know what their value is, and if you take the information here that I'm giving you right now, you'll be able to look at a wall line that's got some existing retrofit work, and you'll be able to say, hey, these UFP 10s can resist this much. I need to add a couple more of this type of hardware to augment it and make it exactly what I want, based on the calculations that I've made. So that's why all this is so important. Now let's go into the shear transfer ties. Exact same thing. Shear transfer ties are all rated in the catalog in terms of pounds that they can resist in Douglas fir. So what we do, we just do the exact same thing. We take our 0.88 multiplier. If we're going into old growth wood, we multiply 0.88 times whatever our Douglas fir value is, and then we end up with this right here. So just an example, Douglas fir for an L90 is 925. We multiply that times 0.88, and we end up with 814. Now, if we're working with a new growth wood, in other words, we look at our mud sill and it's only 1.5 inches thick, and it's redwood, we have to multiply everything by 0.74, and then we get completely different values. So you see why it's so important. If you don't do this in your retrofit designs, you'll come way off. you won't have the right values for your hardware, and then once you figure out how much earthquake force is going to attack a house and how strong the retrofit needs to be, if you don't know the strength of your components, you can't possibly do it correctly. So that's why this is also important. There's another type of hardware called an SDS screw made by Simpson Strong-Tie, and we use those a whole lot, and they are also impacted by specific gravity. So the way these are rated is in terms of the amount of penetration they have into the wood that they're going into. So if you're going into a piece of wood 1.5 inches, you can get in 1.5 inches, it will resist 300 pounds of earthquake force. 2 inches, it'll get 450 pounds. 2.25 inches, 550 pounds. Now, if we're going into redwood, old growth redwood, we have to use this multiplier again, 0.88. And so for this 300 pounds right here, it's turned into 264. 450 is turned into 396. 550 is turned into 484. So that's the impact of this 0.88. Now, if we were going into new growth redwood, in other words, if it's 1.5 inches thick, and it's sort of a newer house, probably 1945 on or something, made out of redwood, then we'd actually use the other multiplier of 0.74, so it would be reduced even more. So these are illustrations of what happens when the plywood on a shear wall fails. The thing we're going to be looking at here is if there's a difference between redwood and Douglas fir in terms of something that will resist that. So here we have, this is our plywood, that yellow right here. The nail is remaining intact, exactly where it should be. So let's say there was an earthquake, everything stayed right where it is. There's absolutely no problem. Here we have nail pullout. And in this case, the plywood has remained, it's still there. The nail and the plywood are connected, but look, it's pulled out of the framing. This is the framing right here. And in this case, we've had complete failure where the nail has pulled through and the nail has pulled out. And, again, in this case and this case, we did have nail pullout, and that is something that we want to avoid if possible. So here we have an actual photograph of it. Here's the, this was the plywood. In this case, it's OSB. Here's a nail here, here's a nail here, and here was a nail here. And it's pulled the nails out. It hasn't pulled out completely, but it certainly, gave that piece of plywood a lot of stress. And this is a partial failure of the shear wall. We can go down and look at this one right here. A very similar situation, except now we have a complete failure, where the nail has pulled out of the framing, and at the same time it's no longer even touching the plywood anymore. It's just pulled out completely. So that is something that we definitely want to avoid. So let's go ahead and see how redwood and Douglas fir compare in terms of their ability to resist that kind of action. So here you can see some nails that are pulling out of a mud sill. This right here is a pressure treated mud sill. The nails are pulling out, as you can see, this nail, they're all pulling out. And we just looked at, previously we looked at the failure of shear walls, and what happens is the nails pull out. And because they pull out, a really big thing to worry about is at what point do they pull out. And in Douglas fir, the nails pull out at 104 pounds of withdrawal force, whereas the redwood is at 75. So for that reason, whenever you're nailing a shear wall into a redwood mud sill, you should always tighten up the nailing so that the withdrawal, strength is equal to what you have in the Douglas fir if you really want the shear wall to perform as intended. Remember, yours only as strong as your weakest link. So if you have redwood in the entire assembly, that redwood will fail before everything else does, so you want to make sure it's good and strong. So I'm kind of taking a survey to find out who knew this information already. Some people did, some people hadn't. I've actually found engineers who had no idea about this stuff. So I'd really like to get an idea if you knew it or you didn't know it, want to know if my videos are helping people, and I'd especially like to know if you plan to use this information in any retrofits you might be doing.